Hello, Assalamualaikum. Okay, sorry for the late. Now we continue our class. Last class we had done on this example, number 2, based on the process monitoring and analysis. Okay, so now I would like to proceed on the monitoring thermal efficiency for combustion system. Okay, thermal efficiency for combustion system where it is a ratio between energy output and energy input. Whenever you mention about efficiency, it is always about out over in. Okay, efficiency is always about out over input. So in this combustion, thermal efficiency, we focus on the energy out over energy in. Energy here means the Q. Okay, we focus on the Q. In thermodynamic textbook, the energy might be described as work. Okay, there are cases it involves the work. So it depends to the system. Now we are focusing on the combustion process only, not the heat engine. Okay, the heat engine, it will involve the work. Now only for the combustion process, where we focus more on the Q. Okay, energy here refers to the Q. Now Q output, we know in combustion process, there will be Q release. Okay, so this is Q out. Q in is from the fuel. The Q generated from the fuel. And make it slideshow. Okay, so that's why here it says heat released during the combustion over heating value of the fuel burn. Okay, heating value of the fuel burn. So Q, in previous chapters, previous topic, previous example, we had done on the calculation of the Q. Be it in constant pressure, constant volume, adiabatic. Okay. Now, for heating value of the fuel burn, okay, we see which is the HV. In this equation, it refers to N fuel multiplied by the LHV. Now, this LHV, where to get? What is LHV? Low heating value. We have LHV, HHV. So, what is LHV and what is HHV? You need to know why it used LHV instead of HHV. Okay, in flue gas, what are the products that you have? CO2, H2O, and 2, right? O2 is behind excess of N. Now, this H2O, if it is in gas form, so heating value involved is the LHV. Okay, if the combustion process release gas, H2O in vapor form, it involves the LHV. If the process release H2O in liquid form, so it is HHV. Okay, why it considered in LHB, not HHB? For example, combustion process in car, is car. So the car, does the car release H2O in liquid form or gas form? Vapor form or liquid form? Car. Do you see water coming out from your exhaust? Water flowing out from your exhaust. Huh? Vapor, right? If water flowing out from your exhaust, then something is wrong with your engine. So it is in vapor form. So that's why it used LHB, because the H2O release is in vapor form. But in power plant, they will use HHB. Power plant normally for the thermal efficiency, they will, the HB, the heating value, and fuel multiplied by HHB. Because the water in the product stream will be condensed in the power plant. Okay, it will be condensed. Let's say furnace to heat up the boiler. So the water vapor released from the furnace after that will be condensed. Okay, so in the power plant, they consider using HHB. Okay, now in our slide over here, we focus on the LHB. LHB because as I give you example on the car engine. Okay. Now over here, M fuel is the fuel that you use. So it depends on the type of fuel that you use. M fuel, the mass. LHB, you can either calculate it or you can directly extract from the properties table. Okay, later we go through the example. Now this is what I explained just now for the heating value. Amount of heat released when a unit of amount of fuel at room temperature is completely burned. Okay, LHB when the water leaves as vapor, HHB when the water leaves as the water condensed to form liquid, which it involves the heat of vaporization. Remember last time the HHB calculation heat formation of water vapor plus the HFG. This one in chapter 3. Okay, so it involves the heat of vaporization. That is HHB. Okay, now we go for the example. Let me put side by side with the properties table. Okay, this is what I meant just now. From the properties table, you can also extract the LHV and HHV. But here the unit is in kilojoule per kg. Okay, A27. So let's say your liquid, your fuel is propane. So LHV is this value with the unit kilojoule per kg. Okay. Now let's try this example. Coming up. Now, this example, we have propane as the fuel. Propane C3H8 operates with excess air. O2 concentration in the flue gases is 2%. Okay, measured after removal of the moisture in the combustion products. So here it means after removal of the moisture. What do you understand from this? It is in dry basis. Okay, so this O2 composition in the flue gas 2% dry basis. Okay. In this statement, it doesn't straight away mention dry basis. It mentioned after removal of the moisture. So it is in dry basis. Now, flue gas temperature is 650 Kelvin. It asks you to determine the equivalence ratio and the thermal efficiency of the boiler, where the fuel and air enter at 298. Okay, so equivalence ratio, like last time, it is, you can use the value of the A actual over A start or A start over A actual. You remember? Start over actual. So A start over A actual. How this come from? From the AF ratio. Okay, first thing first, we answer for the equivalence ratio first. Huh? To get the A start, we can get from the equation x plus y over 4. A actual, you will need to find out from the general combustion equation. Okay, as always, what is the combustion equation? We have propane as the fuel. Okay, we have two unknown, the A actual and the B. Okay, generate the equation, the two equation using the O balance. Okay, and another one is using this info, the 2% of O2. So the 2% of O2 is 0.02 B over the N total. N total over here is the dry. Okay, so the N total is 3 plus 4 is not included because it is dry basis. So 4 is not included, plus B plus 3.768. Okay, so from the O balance, you will have okay, from here you can get another equation. First equation, second equation. So combine them, you will get what is A and B. Up to that, any question? Okay, if you have the slide, it already shows you the solution. Now this is the first equation. Sorry, this is then you have this another equation. Okay, rearrange it, you will get your A and B. Your A is around 5.482, B 0.482. Okay, roughly around that figure. Now from there, this is A actual. 5.482 is A actual. The one that you calculate is A actual. Find your A stoic from the equation. then your equivalence ratio, you will get around this figure, 0.912. Okay, after you obtain the equivalence ratio, we can proceed to determine the thermal efficiency. Any question on the equivalence ratio? Okay, for the thermal efficiency, this is the equation involved. Okay, so the Q is calculated from the equation, from the enthalpy equation. Okay, where the product minus reactant. Okay, this one, as usual, you find out what is the info of the component. Okay, we have component over here. You have your fuel, C3H8, product gases. Okay, find out what is your HF. H at 298, then H at outlet. H at outlet, just now it was given as is it 650. Okay, so H at 650 kV. Okay, this one you should already know how to find it. Now I want to focus on this part, the LHV. The LHV from your notes, it shows LHV is equivalent to negative QC. Okay. Now, from the combustion equation just now, we have the full combustion equation. So we take the start, take the start combustion equation at start. So here you will have heating value just now when the fuel is completely burned. So we take the start. Now from here to find the LHV, we can extract from the properties table. Propane, liquid propane, so the LHV 46340. Okay, from the properties table, the LHB is this 46340 kilojoule per kg. The Q that you calculated earlier, the unit that we always use is what? Kilojoule per kilomole. Okay, so the LHB over here is in kilojoule per kg. Now, how to convert to kilomole? Here we have the molar mass. Okay, using this molar mass. So the LHB multiplied by the molar mass what do you get? What do you get for LHB using the inputs from the table? The LHB multiplied by the molar mass. It's not right. Okay, this one is from the table. A20. Which table is this? A27. Okay, let's say in the table you cannot find the LHB. So how to get the LHB for a certain fuel? Okay, now let's say the LHB is not obtained from the table. LHB is equivalent to heat of combustion. So here it involves the product minus reactant. LHB over here, we focus on the fuel, because here is fuel. Okay, fuel. So fuel over here is the propane. Now this is the product. Okay, for the LHB, fuel amount of energy released when fuel produce H2O in gas form, vapor form, LHB. So now the fuel, the amount of the fuel, heat of formation of the fuel minus product. Sorry, reactant minus product. So reactant is the fuel, the propane. Now the HF of the propane, we can extract from the table. It will be this value. Heat of formation. So here of formation, it is in table A26 for propane 103850. Okay. Now from there, minus the product. Product over here, CO2, H2O, and N2. Okay, we have 3 moles of CO2. So HF of CO2, find out the HF of CO2, which is this one. Okay, then the H2O in gas form, this one. N2 HF is 0. Okay, so we will ignore the N2 because the heat of formation is 0. Okay, so after that, plug in all the infos for CO2. Okay, 0 here is the N2. Because heat of formation of N2 is 0, so that's why 0. Okay, from here, when you calculate, you will get this figure. 2 kilojoule per kmol. This is for LHV from calculation. Okay, so from calculation and from the table, slightly different, but not so big different. You see, from table and from calculation, both can be used for the LHV. Okay. Okay, try to proceed to find out the Q over here, where you should find the infos using this table. Then this is to find the Q. Okay, the Q out. Okay, try to calculate and you will get one figure of Q. From that figure, divide by the N LHV just now, which is the Q input, then you will get the thermal efficiency. Okay, now try to do that. That one is Q minus.
You want.
The LHV. can narrate it. Okay, for the LHV, this one, for the product, it involves only the heat of formation. So it doesn't involve any sensible heat. Okay, you notice this is the heat of formation of the CO2, H2O. Only involve the heat of formation for the LHV. For the Q, it involves the sensible heat at the T outlet and the T at reference. Okay, on the side over here, don't get confused. Basically, Q is product, finished product. Q is product minus reactant. Okay, here it is negative Q. So that's why they just play around with the equation. Okay, for the thermal efficiency, we need the numbers only. The sign is not that important for the efficiency. Okay, the negative out here, when you calculate your Q, you will get somewhere negative. Negative means exothermic. So that amount of energy is being released. Okay, so for thermal efficiency, the sign is not that important. We will need the figures, the amount. Okay, once you get the Q, divide by the LHB multiplied by the MQ. The efficiency you should be getting around 85%. which has been uploaded. Within speech and transcript.
Yes. About the things. And session.
Okay, if you're done, try to do this. Just now it is propane, now it is butane. Okay, butane. Concentration of O2 in the flue gas is 3% instead of 2% just now. After removal of the moisture, again it is in 3% of the dry basis. Flue gas temperature is 800 degrees C. We try to compute the equivalence ratio and also the thermal efficiency. Similar step as the previous. Butane is what? C4H10. Okay, roughly for A, you should be getting 0.8671 for the equivalence ratio. And for the efficiency, roughly around 77%. Around this figure. Try to do until you get the answer. Okay, before I forget, Friday's class will be fully online. Friday's class fully online, and please wait for my announcement in CN. Okay. Any question before we end the session? You can proceed to calculate the thermal efficiency. Yeah?
What's the benefit?
Okay, we have any question before we end the session? Okay, hopefully you understand how to calculate the thermal efficiency. In this case, we are using constant pressure. We assume constant pressure. Okay, try to figure out how will it be if it is constant volume. You will be using different kind of equation, and it will take a longer calculation. Okay, so that's all for today. Thank you.